Science Nines, and welcome to topic 1.3 of the Space Exploration Unit, using technology to see the visible, or shall I say the hardly visible, when it comes to looking at stuff in the night sky. Um, Pretty much we've discussed this technology already in the unit. We discussed telescopes, which were designed as early as 1608 by Hans Lippershey, a German glass or lens maker. He designed and created the first telescope. And from that initial discovery, we've had essentially now 4 centuries of incredible discoveries, from the night sky, from space, being able to peer up into the stars. Um, Telescopes that use essentially visible, that can see visible objects in the night sky, things that we can technically see ourselves using the visible light spectrum. We call these telescopes optical telescopes. Now, there are all sorts of telescopes out there. There are telescopes that will see, visible light. There are telescopes that will look at infrared light that we can't see. There's even telescopes out there like Chandra, which is a telescope in orbit around the Earth that actually detects X-rays. There's also telescopes that pick up radio waves from outer space as well. So not all telescopes are looking for things that we can see essentially in the visible light spectrum. But those ones that do are considered to be are called optical telescopes because they're looking at the visible light spectrum. There are two types of telescopes in this category. There are refracting and there are reflecting telescopes. The earliest telescopes that were designed were refracting telescopes that use lenses. And essentially what refracting means is just a fancy word for saying that you're bending something. In this case, we're bending light. If you take a lens is going to bend light as it comes to it because lenses have different thicknesses at different portions. That means that certain light waves are going to come through quicker. Some are going to move slower based on the thickness of the glass or of the lens, and that's going to actually cause the light in this case to bend. So that's how lenses work. And these would be the telescopes like Galileo would have used, like Tycho Brahe would have used back when they were, essentially discovering the fact that we lived in a heliocentric solar system or a heliocentric universe. But the problem with these telescopes is they're limited. You can only make a glass lens so big, and you're really restricted to a lens diameter of about a meter. Once you get past a meter, the lenses get too big, too bulky, they're too tough to make and to make them perfectly round. So there is a limit to the size that you can make a refracting telescope. So Newton came along, Sir Isaac Newton came up with a different approach to telescopes, and he used a process called, or a telescope known as a reflecting telescope. And these reflecting telescopes are still used by scientists today. And what a reflecting telescope does, as you can see in the diagram here, if you've got your notes in front of you, essentially you've got a larger opening and a mirror at the bottom of the telescope will reflect the light back, hence the name reflecting telescope. It will reflect it to a smaller mirror inside the telescope, which will then will basically point toward the eye of the operator. Now, the beauty of reflecting telescopes is you can make mirrors much larger than 1 meter. Mirrors can be, and you can also, what a lot of telescopes are now doing are they're using segmented mirrors. So you could have, let's say, 50 mirrors all put together to create one giant mirror. So you have a much larger mirror to work with, which lets more light in, which gives you increased resolution, resolving power, which allows you to see things that are even further away. So it's for this reason that we pretty much are only using the big telescopes on the planet right now are all reflecting telescopes. Could you go out and buy a refracting telescope? Yeah, but they're not as powerful and they're certainly not as common. Right now, we're sort of in the age of the reflecting telescope. Galileo, Brahe, Copernicus, all these guys that were doing that stuff back at I guess not Copernicus, but Galileo and Brahe for sure, that would have been the age of the refracting telescope. So we're dealing more with reflecting telescopes because you can have much better resolution using them because the mirrors get bigger. Another way that you can increase the resolution of a telescope, how sharp it picks up an image, is you can actually piggyback more than one telescope together. The way you can think of this is, imagine if you took several computers and you daisy chain them together to increase the processing power of several computers, and you put them all together. You network them together. Well, this is sort of what we do with telescopes as well. And in the process that I'm referring to is called interferometry. I can never say that word, but it's essentially interferometry is a process by which you take more than one telescope, you put them in very close proximity to one another, you all point them toward a particular part of the sky, and because you're using more than one telescope, you're getting the resolving power of all those telescopes sort of combined. An example of this would be in Hawaii. If you've ever been to Hawaii, to the Big Island of Hawaii, there is a mountain there. It's the tallest peak in Hawaii, called Mauna Kea. It's about 13,000 feet above sea level, so a pretty big mountain to be an island that close to the ocean. On the top of that mountain, there's several telescopes, and two of them are labeled Keck 1 and Keck 2. And these are two telescopes that have 10-meter mirrors. They're segmented mirrors, but they're essentially 10 meters in diameter, so pretty big. And they are only located about 85 meters apart from one another. So by doing this, and you can now take these two telescopes and point them to one object in the sky, you can vastly increase the resolving power that only one of those telescopes would have. If you're using both of them on the same object, it vastly increases the sharpness, the resolution of the image that you're creating by having that process of interferometry. A couple of exciting things about telescopes coming up in the near future. 2025, the ELT is coming out, which is called the Extremely Large Telescope, which is going to be in the Atacama Desert in Chile. It will be the largest telescope on Earth. It's going to have a diameter of its segmented mirrors. It's going to have a segmented mirror diameter of 39.3 meters, so almost 40 meters in diameter. It's going to be comprised of 800 segmented mirrors, and it's going to produce images that are currently 15 times sharper than probably the most famous telescope in the world, and that's our good old Hubble Space Telescope that's out in space. Now, Hubble is a very famous telescope because it's gotten some amazing images. Now, it's not because it's got the largest diameter of lens. Hubble has the advantage of being in outer space. And because it's in outer space, it can avoid the problems of looking through the Earth's atmosphere with the distortion of the atmosphere. The problem with ground-based telescopes that are optical is they're based on, you need a clear night, you've got to find a place where there isn't a lot of cloud cover, clear skies, not a lot of atmospheric pollution. So there's only a few places on the planet where you can put these telescopes to maximize their ability. Like, for example, we've got those two on the top of Mauna Kea in Hawaii. Very little light pollution out there. You're in the Pacific Ocean, not a lot of pollution in the air. You're above the cloud cover for most of it, so you've got clear skies at night. Atacama Desert, the ELT that I just talked about, the 39.3 meter telescope that's being built there for 2025. That's one of the areas that has the least amount of rain in the world, and again, not near any major urban centers. So you're going to get very clear skies. But if you can get out of the Earth's atmosphere completely, go into space, you can have a smaller telescope that's going to give you incredible results. And Hubble, just to put it in perspective, has been able to look at objects, and I mentioned this earlier in the unit, it's been able to look at objects that are 13.4 billion light years away from Earth. So we are only a million light years away from being able to see far enough back in time that we can almost see the Big Bang. So this is kind of exciting stuff that we have this ability, again, to see back in time, because remember, light that travels 13.4 billion light years to get to Earth, we're looking at something, when we see it here on Earth, it's actually 13.4 billion years ago. We're seeing the light that's that old. So we're not looking at what it currently looks like. We're looking at something that it looked like 13.4 billion years back. So if we can even see further than that, if we can get a bigger space telescope, that would actually give us even more of a chance to see further back in time and further into the universe. And that's exactly what's proposed. By the way, Hubble's mirror is only 2.4 meters. Hubble, just the size of it, it's about the size of a large school bus. So if you see your school buses outside of MCHS, that's basically the size of Hubble, and it's got a 2.4 meter mirror inside of it. So even though it's got a fairly small mirror compared to, let's say, Keck 1 and Keck 2 on Earth, which have 10-meter diameter mirrors. It's out of the Earth's atmosphere, so it has a much clearer picture of the universe. That said, there is a new telescope that's being proposed to get out into space here very soon, and that's going to be the JWST. That's the James Webb Space Telescope. It's set to launch in 2021. It's going to have a segmented mirror that's going to have a diameter of roughly 6.5 meters in diameter. That's going to be 3 times larger than the one on Hubble, and it's going to be placed into a much higher orbit than Hubble. Hubble is fairly close to the Earth. The JWST. That's what I'm trying to say. The James Webb Space Telescope is going to be roughly 1.5 million kilometers away from the Earth, compared to Hubble, which is only 550 kilometers away from the Earth. So it's going to have a much higher orbit around the planet, well out, that will give it even less of a less atmospheric or light pollution from the planet per se, by getting it out that much further. That's it. That's about everything about telescopes. Before I go today, watch this video, which is a great little recap on telescopes. What's the homework on this? Pretty straightforward. I'm going to get you to questions 1 to 9 on page 439 of the Science in Action 9 textbook. That's my conversation for today. Won't you join me next time when I discuss topic 3.2, which is using technology to see beyond the visible. How do we now see, using telescopes, as I mentioned already today, to pick up X-rays, how to pick up radio waves, infrared waves. We'll be discussing that in our next discussion. Won't you join me? Thanks for tuning in.